Very good afternoon to friends in India, Asia, and good morning to our speaker and friends from Europe. So I'm really delighted and very happy to welcome Professor Karin Everschor-Sitte from University of Duisburg-Essen. And many thanks to Karin for kindly agreeing to give this lecture in this webinar series on spintronics. So first of all, on behalf of my co-convener, Dr. Prof. Singh, and my team, we really express our thanks to you and also other participants to join this seminar. So a brief introduction about Karin's academic profile. So she is currently working at University of Duisburg-Essen as a professor in theoretical physics. And I should just mention that Duisburg-Essen is the place where I got my PhD. And this is like my second home. I'm really happy to have a speaker from my alma mater university. Okay, so before, so I think she had worked at several places. So she got her PhD in 2012 from University of Cologne in Germany on the topic current-induced dynamics of chiral magnetic structures. So mostly skyrmions, emergent electrodynamics, and spin transfer talks with Professor Joachim Gross. And then he did postdocs, she did postdocs at several places. For instance, 2012, 2013 at Technical University Munich in the group of Professor Christian Fleider. Then 2013, 2015 at postdoc via DAD fellowship at University of Texas at Austin in Professor Alan McDonald's group. And 2015-16, she was working with Professor Jairo Sinova at University of Mainz. And then I think 2016 onwards, 2016 to 2021, she was the head of ME Noether Research Group with the topic topological wheels in spintronics at University of Mainz, and recently moved to University of Duisburg. And she has won several recognitions, awards. For instance, I will just talk a few. She got the Hertha Sponer Prize 2018 of the German Physical Society, DPG, awarded to a female scientist for outstanding scientific work in the field of physics. She has been worked as a member of the steering committee of the German priority program, Skyrmions SPP 27, and she has also worked as scientific coordinator of the Spin Phenomena Interdisciplinary Center, SPICE, which was established by Professor Jairo Sinova. So with this brief introduction, I again welcome you, Karin, to this webinar series and everyone. So just to mention that during the lecture, we don't take questions. If you have any questions, you can write it in the chat box or just say, I have a question. At the end of the lecture, I will take all the questions one by one. So it's all your, Karin. Looking forward to your lecture. Thank you so much.
Thank you very much for the kind introduction. And it's a pleasure to be invited to the seminar series online. The title of my talk is Magnetic Skyrmions for Unconventional Computing and Revealing Latent Information. So let me start by introducing magnetic skyrmions and then talking about skyrmions for unconventional computing, and also about, in the last part or in the second part, about data analysis. How can we maybe improve or work with data analysis to have better tools for microscopy. So on the skyrmions for unconventional computing part, I will briefly mention skyrmions to build a reshuffler device for stochastic computing, a work where the experimental part has been done by the group of Matthias Kloy, where they have built the reshuffler device, a prototype device for reshuffling bit information. And in the larger part, I would like to talk about skyrmions for reservoir computing, an idea that Georgian Buryanov and I have been pushing forward since a couple of years now, and where we find that kind of like disturbed skyrmion systems might be a version to do reservoir computing. And in the final part, I would like to talk about this data analysis project, which we have done in collaboration with the data scientist Ilya Hurenko, and also with David Rodriguez, Terence O'Kane, and Susanna Gerber. And let me mention that it's a very interdisciplinary project where Terence O'Kane, for instance, is a climate researcher, and Susanne Gerber is working in the biomedical department, also with an informatics background. So let me start by explaining what is a skyrmion. And when you just look it up into Wikipedia, then you find that a skyrmion is a homotopically non-trivial classical solution of a nonlinear sigma model with a non-trivial target manifold topology. And I think what we can all get out of this is that we are dealing with an object that we can define rather precisely mathematical. And as such, it can occur in different regions of physics. So originally, it has been actually introduced in the field of particle physics by Tony Skyrm. And in this talk, I will not talk about particle physics, but I will talk about magnetic skyrmions. And here you see one example. So the color code is chosen such that it just helps you to understand this figure better. So each of these arrows tells you what the local magnetization direction is. And when an arrow is red or pinkish, then it's pointing upward. And when it's blue, then it's pointing downward, and yellow somewhere around the equator. So how can you obtain such a skyrmion? You can start from a hedgehog, or more from a mathematical hedgehog where you have all outward pointing spins. And then you open this hedgehog a bit like this animal would open and project it down to the sphere. Or you can look at it more from a cartoon picture or a movie picture done by Jan Marcel, previously Jan Müller, where you kind of open the hedgehog, project it down, and then you obtain your skyrmion. So you can get nail-like skyrmions where you just open it, or you can also have different type of skyrmions, for instance, block-like skyrmions, where you first take a comb this hedgehog a little bit, and then project it down, where you get this additional in-plane twirling structure. So in general, there are more than just these two. So in the recent years, there has been a full zoo of topological and non-topological magnetic textures being discovered. And here is just an example of some of them. And all of them have very interesting physics. But so far, we have just talked about mass. So if we look a bit more into the physics part, then for magnetic skyrmions, then we can actually find some very early on theoretical predictions from Bogdanov and Jablonski in 1989. But the first experimental observation was in 2009 in the group of Christian Fleiderer, where they have seen skyrmions in a neutron scattering experiment. And here you see the momentum resolved part, which in real space transforms to a skyrmion lattice. So magnetic skyrmions occur in systems with broken inversion symmetry, and you can understand this quite easily because if you want to go from this spin towards the middle, then you can turn either left or you could twist to the right. So you need to break inversion symmetry either spontaneously or directly by the material. And this explains why they occur in so many different magnetic systems, because what you need is basically one interaction scale that prefers to have an alignment of the spins. So this you can see when going around the circumference, and another one that would like to have them canted. So this is when you cross the middle here. So therefore you can have them in metals, semiconductors, insulators, bulk and thin films. You can engineer their size by putting in more of these twisting interactions. They typically become smaller. Or if you, and the breakthrough in the field was that they are not only observed at low temperatures, but also even above room temperature. And another interesting fact is that they are detectable by various experimental techniques. And by now they occur in systems that are used in devices. So magnetic skyrmions you can also create, manipulate, and destroy by different techniques. And this finally makes them quite interesting. So let's go to the questions, why are they interesting? One is this mapping here. So one is that this topology that is behind this mapping once to the sphere gives them some sort of additional stability. The other part, what I've just mentioned before, was that they can be rather small and they have been observed above room temperature. And there are also more interesting physics effects also. So one thing that we have found rather early on, so during the time I did my PhD thesis with Achim Roche, the experimentalists in the group of Christian Fleider have found that when you take a skyrmion lattice system, then you can move these skyrmions by very low current density, so 10 to the 6 ampere per square meter, where the typical order to move a domain wall would be 10 to the 11 ampere per square meter, so 5 orders of magnitudes lower. They also have a quite interesting dynamics because of the Magnus force. So when you apply current to the system, they do not only move straight, but in case you have a twirling ball, then they also get a force in a perpendicular direction, which is in soccer called Magnus force. And here an analogy you also have when you apply an electric current, then they do not only move straight, but you also get these deflecting forces, which are the Magnus forces. So finally, you get a skyrmion Hall effect. They are also interesting for spintronic applications as they occur in device-relevant systems. So when we look at skyrmion-based devices, so let's say we have our skyrmions and we look at skyrmion-based devices, then what we can say is that probably the most studied potential application is the skyrmion racetrack memory. So the racetrack memory itself was suggested by Stuart Parking, and here you store the information in different types of domains that you can shift or move through the wire, and thereby also have a read and write element to store information. So there has been the suggestion by Albert Fair to put skyrmions on the track. And yes, there are some advantages. So for instance, these skyrmions can move around obstacles, so they would not get stuck at the edges as a domain wall would get. But as we have just seen, there's also the skyrmion Hall effect. So this might be eventually detrimental to such a device, as a skyrmion would not move only along the wire, but also has a perpendicular component and could eventually be destroyed at the edges. So therefore, there has been a lot of work on how to get rid of this skyrmion Hall effect. And by now there are probably even more. So there's a short overview of some of the works that are existing. And so far, I would say one can group them into 2 categories. So the examples shown on the left use basically the equation 1 plus minus 1 is equal to 0. So what do I mean by that? Here, the idea is to take 2 skyrmions, and one being kind of opposite than the other. And the one on the top, for instance, would go straight and feel a force to the right, and the one on the bottom would go straight and feel a force to the left. And since they are coupled, the forces to the right and to the left cancel each other and finally get a straight motion. So the same is true for soft skyrmions, so synthetic antiferromagnetic skyrmions, as well as skyrmions in antiferromagnets. And another part is that if we use an additional symmetry breaking, so for instance, something that you can see here for in-plane skyrmions, where you have the outer magnetization direction, and then you can apply the current at a certain angle to that. So you use an additional symmetry breaking to play with the direction in which the skyrmion moves, and thereby you can also reduce or get rid of the skyrmion Hall effect. So all of this is fine, but when we think about it from a different perspective, then what we have done is we took an existing device concept and just replaced it with skyrmions here. Another question that we can ask is, let's say we have these skyrmions, what would be a device that optimally uses the properties of the skyrmion? And here we can think of the domain wall just being a one-dimensional object. So you just need to know the position, and therefore a one-dimensional device might also be optimal because you just want to shift the domain wall. But for skyrmions, actually they are particle-like. So they can move in 2 dimensions in principle. So restricting the motion to 1 dimension actually reduces their possibilities of applications. Also, we know that skyrmions can breathe or have excitation modes, which are in such a way also not used. So we can think of eventually having two-dimensional devices, and there's one suggestion by Jan Müller to basically build a two-lane racetrack, but here he still puts the information finally into one dimensions. So we have been working on ideas on how we can employ skyrmions in two dimensions. And I would like to mention briefly stochastic computing. And here the idea is that one has to, in stochastic computing, has some random bit signals, which have to be, should not depend on each other. So, and what you need for that is to reshuffle eventually the information if they are, if there's some sort of dependence. And for that, you can build a Skyrmion reshuffler device. So the idea is kind of like as shown on this cartoon from Andreas Donge, that you have Skyrmions incoming, they provide a signal, as I'm going to show in a minute, and then you use kind of a mixer so that they get out at different times. So this is a concept that has been suggested by Daniel Pina while he was working in the group of Julie Collier, and has been realized experimentally in the group of Matthias Kloy, where you have an incoming signal that is described by skyrmions going in to either of these chambers, and then you get these skyrmions reshuffled in these chambers, and then they exit at different times, and this builds your outgoing signal. So, but as I said, I would like to spend the main part of the talk actually about reservoir computing. So let me go over to reservoir computing and give you a short introduction into the field. So the field of reservoir computing has actually emerged from the field of artificial neural networks. And in artificial neural networks, you have some input nodes, you have some intermediate nodes, and you have some output nodes. And typically you have some sort of recursive neural network. And what has been noticed is that under certain type of training, actually only some of these weights here have been trained. And if they were close to the end, then from this observation, it has emerged a new field, namely the field of reservoir computing, where the idea is that all of these gray connections here you leave fixed, and only these orange ones here, which are just the connection to the output nodes, need to be trained. So in reservoir computing, the idea is not to fully solve a problem, but to map a complex problem to a linear solvable one. So, and let me then explain the functionality of the reservoir, or what is the idea behind it. So first in words and then in a picture way, the idea is that the reservoir projects different spatial temporal events into a sparsely populated high-dimensional space where they become easier to recognize and categorize. So looking at that, you have some input space, and then the reservoir projects them into a high-dimensional space where you can then draw hyperplanes to separate the data. Okay, and what could such a reservoir computing system be useful for? It allows you to recognize and classify spatial temporal events, such as speech recognition or sensor fusion type of applications. And the advantages are that you can train for different output errors and different features simultaneously. For instance, if you take speech recognition, you could train for having a male or a female person speaking, the word that they are saying, or whether it's a child or an adult. And another really key advantage is that you don't have to know any details about the reservoir. So if we don't have to know anything about the reservoir, then we can put a black box here. But for sure, the reservoir has to fulfill this image here on the left. So it has to provide this working principle. And you can also put this working principle here in the left into words. Namely, this one needs to be a low dimensional space. That one needs to be a high dimensional space. The reservoir response must be nonlinear to input, because otherwise the data wouldn't separate. And you need to have some short-term memory in the system, because in case you want to do some temporal recognition. But if you summarize these words as a physicist, then what you can actually do is, what you need for a reservoir is a nonlinear complex system with a short-term memory. And this allows them to just put material there. So you can do pattern recognition with matter, as most of our systems that we study are nonlinear, complex, and have a short-term memory. And when I say you can put basically any system here, that's also what people have done. So people have done a pattern recognition with water buckets. So they basically took a bucket of water and put some pellets on top and then resolved patterns on the surface of the water. You can also use optical systems as well as spintronic systems, as have also been used by the group of Julie Collier. So before I tell you what we want to use, I would like to first give you a bit of an overview of how I see reservoir computing. So in my view, one can go a little bit away from this idea of building like individual nodes and connections, and one can see it more as a whole. So what you need are some input data that you want to classify and categorize, for example, people saying 1 or 2. And then you need to bring this input data into a language that your system understands. So in my case, this could, for example, be voltage signals. And then you need to feed your signals to your system at hand, which in my case is a spintronic system, and it's going to be a skyrmionic system. And then you need to define readouts in your system, which define the high dimensional space. And I'm going to show for the skyrmionic systems 2 examples how one could do that. And in this high dimensional space, then you use your computer and you do a simple task on the computer, namely the data separation by linear regression, and thereby you categorize your output. So the system that we had in mind, and by we I mean George Buryanov and myself, was using complex skyrmion structures, so-called skyrmion fabrics, as a reservoir. And then to put kind of voltage contacts on top of the reservoir, and then feed a voltage signal into the system. And the idea that we had in mind was basically relying on a similar picture as this one, where you have a current filled with rocks and stones. And now if the water current will for sure find the path with the lowest resistance, and if a current is strong enough, it might also shift or excite the rock a little bit, and thereby then allow for a new pattern to arise. So this is what we have looked at, and we went in very simple steps. So as a very simple system, we considered 2 voltage contacts, and we put eventually a pinning center in the middle, and we studied magnetization-dependent magnetoresistive effects, such as the anisotropic magnetoresistance. And just one side note is that the magnetoresistance have been shown in experiments strong enough to find the difference between 1 or 2 skyrmions, etc., being present. So it's not something that is not out of the scope of measurements. So we've been looking first as a single skyrmion, and then we looked at the current that would arise if you have an AMR effect. And here's the current that we computed. And to just better see the effect of the skyrmion, since the current flow even in a magnetic system would have some sort of shade, we subtracted the ferromagnetic background of the current and just looked at what the skyrmion does. And what we can see is, so purple means less current, green means more current, that through a Bloch skyrmion, the current likes to flow, where through a Néel skyrmion, it likes to go around it. So if we scale this up and not just take, if we consider one skyrmion as a device and pin it, and now apply current, then we know that these skyrmions get excited, or they get larger and stretched by the current, and then we can plot the resistance as a function of the applied voltage, and then we see some sort of nonlinear IV characteristics. So that is the first signal that skyrmions behave as nonlinear resistive elements. So if we scale this now up to a lot of skyrmions, then we see these current patterns that resemble, so shown on the bottom part, that resemble these magnetic patterns shown on the top part. So the skyrmion reservoir that we have been using for this work is shown here. And here you see the magnetic structure with the 2 contacts being enlarged for visibility. And here you see now the current flow that arises because of these skyrmions in a bit of a different color code. And something that we can immediately see from our requirements, where we need a nonlinear complex system with short-term memory for our reservoir, we can see that we have a complex system. Okay, and what we need to also test for physical system, that there's some sort of stability. So the skyrmion must not displace significantly from the reservoir to work properly. So this we have tested, or this we do in the simulations by pinning the skyrmions through a grain pattern. So this is something that would also be present in experiments, that you have some sort of grains that pin these skyrmions. And then if we apply currents or thermal fluctuations, then we find that the texture does not change too much. So you see the wanted effect, that these are wiggling around, which change my resistance in a complex way. But when I turn off the drives, they go back to the original state. So here are now the results for the Skyrmion reservoir. What is plotted here is time. And in blue, the voltage signal that we have applied. And we have applied, as a simple example, either a sine wave or a square wave. And in red, we have the resistance signal that is measured. So here, first of all, what you can see is that the resistance signal to the sine is different to a square. And the other thing is that you can see is, even when we turn off the drive, there's still a short-term memory in the system. So even if the sine wave is off, it still needs some time to relax back. So from our requirements, we now have complex with short-term memory. Okay, what we still need is nonlinear. And one thing that we observe is that the resistance changes here are really tiny. So what we have done, instead of just applying one pulse, we have applied a train of pulses. So lots of sines and square waves in a sort of different shape pattern. And something that you can see is that these resistance signals are now much, much larger. So red is still the physical response, and golden here is plot the signal that you would get when just superposing these small signals, so the linear reconstruction. So what we see in this plot already is the nonlinear part. So now we already know that we have a nonlinear complex system with short-term memory. And as I've argued before, if we have such a reservoir system, then we are able to do reservoir computing with it. So we should be able to disentangle the patterns based on the history of the pulses that have been applied. And if you just look at this plot, we can first do it just by eye. So just looking at it, you might find 4 different signals. For example, this one here, where you see kind of a certain shape, which arises whenever you have a square wave preceded by a sine wave. So thereby you see these 4 different shapes, and this we can already do by eye, so we have proven that it works. But let's see if we can do this a little bit more elaborate and going even more back into the past, because here we go just one step into the past. So what we have done, and now I'm going to show you how to define this output space. You can do it on version 1, which I'm explaining now, via time tracing. So that means that you just measure the signal and you just mark the height of the resistance or the resistance size at different times. And just measuring one signal, we want to know not only about the pulse now, but we also want to go back into the past. So we've called the preceding one latent and the one even before the past pulse. So how does it work now? We use these measured values as an input to classify, train a linear classifier, which then gives us output about the past, latent, and present pulse. So we train it with some certain data where we know the results, and then we test our data for the prediction. So, and what we can see is that as a function of these resistance trace samples, so that's probably very natural. If you just take one spot, then it doesn't have so much of a predictability result. But if you take more, then at some point it saturates. So around 20 resistance trace samples, it saturates a bit. And then we can recognize the current pulse with almost certain the latent pulse, and also with 90% the past pulse. So if we now want to do a different scheme, because that's the advantage of our system, we are not only complex in time, but we are also complex in space. So what you could do is kind of locally read out the state, for instance, by just doing a magnetization measurement in these black boxes here as indicated. Then you can use these ones as output and still train your linear classifier. And the cool thing is then that you don't have to do a measurement over time. So a single measurement will give you input because of the time correlations that are in the system about the past. So we have done this. And now you are free to take the picture whenever you want. So either with 0 offset before the pulse started. Of course, then you don't learn anything about the present pulse that is going to come, or with some certain delay time. And then we already see that we can classify the present pulse very nicely. And we can also get information about the latent pulse. And we also still get a certain type of recognition rate about the past pulse. So now I've shown to you that these Skyrmion fabrics allow for nonlinear complex system with short-term memory and allow therefore to do reservoir computing. I've shown you reservoir computing on a very, very simple example, showing just sine and square wave pulses. What is good about using magnetic systems or Skyrmions for reservoirs? Well, they are rather small, so they can be on the nanometer length scale. The energy consumption we estimated to be in the microwatt regime. And what is good about our system is the high complexity, the many degrees of freedom that we internally have directly implemented into the system, which help us for the recognition part. And what we are doing now is we want to go beyond 2 contacts. And for this, we are working with the Mumax team, who has written a much faster better code. In particular, I would like to highlight the collaboration with Jeroen Mulkers and Jonathan Lilliat. And also we are more quantifying the reservoir itself and its performance. So this is the work currently done by Jake Love, my PhD student. So with this, I've finished the part about reservoir computing. So let me come to the last part. Data analysis, new tools for microscopy. And for this, I would also first like to give a bit of an introduction. So a lot of projects are motivated by Moore's law coming to an end. And at least economically, this is already true. So even if we can make chips smaller, they do not necessarily become very cheaper. So there has been a trend that if we make them smaller, they've become more expensive. So, and a lot of us say that we need new approaches, but so far no one really knows what these approaches are. So in this talk, I've motivated Skyrmions for unconventional computing, or more generally for computing with material. So improving hardware for computing and eventually being spintronics based. And some of these concepts, depending on what you look at, might even require going back from digital to analog type of information storing, which let's see if this one will come through or not. So while all of this looks a little bit bad, we need new approaches and no one knows what we really have to do and which approach will make it. Still, when we look at computer science, there has been tremendous progress, also touching our daily life. And this is based on machine learning. And some of the key ideas are more than 50 years old. And an enormous part of the progress has been relying on the computational power that we have available by all the graphic cards now. But something to not forget is that the field of machine learning often has some assumptions underlying. So depending on which codes you use, there is, for instance, the IID assumption, which in physics is typically not always fulfilled. For instance, when you look at Skyrmion diffusion, like shown here, which is something that we looked into the reshuffler project, then you do find that Skyrmions like to stay more at certain places than at others. So we have inhomogeneity in the system and not every space is identical. And very often there's a Gaussianity assumption behind it. Also, the field faces a couple of problems in terms of that frequently you need large data. So there's also the need to develop tools that work for small data. You have the curse of dimension, which happens when you deal with large dimensions. Overfitting is a problem. And last, let me mention that at least for us physicists, it's very often the case that not all information is accessible. So you do have some certain latent effects. And what I mean by that, I would like to explain with this picture here, which is a very famous picture that you have probably seen, and a very expensive picture. It shows the first picture or first image of a black hole. And as you know, we cannot just look at the black hole directly. So what you see is the latent impact the black hole has on its surroundings, so on the data. And to get such a picture, what you needed to do is basically have progress in telescope, so on the experimental part, and on the data analysis part. So to be a bit more precise, lots of telescopes have been, the results of lots of telescopes have been put together. And on the machine learning part or on the data analysis part, Gaussian mixture models have been used. So Gaussian mixture models, without introducing them precisely, they are not very cheap in the sense of computational cost. So if you make the data size larger, they have a polynomial scaling in every iteration with the data dimension. Still, they belong to the most popular latent inference methods. And just to have a feeling of what this means, if you just type Gaussian mixture model into Google Scholar, then you will find about 1.8 million entries. Whether when you just type magnetic skyrmions, then you will find the 17,000 entries. So these are really widely used. And but still they are quite expensive on computational costs. So there's a bit of a need of developing low cost tools for the extraction of latent pattern. And this, and here I really would like to highlight the cooperation with Ilya Horenko, is something that he and we have been developing together. So low cost, meaning that the iteration costs do not depend on the data statistics size. And we came up with two physics-inspired computational tools. The latent entropy, which tells you something about the stochasticity or the predictability of your system, and the latent entropy, latent dimension, which encodes the memory of the system. And before I tell you more about these methods, I would like to show you an example. And it's a method that we have been developed for just some sort of video data. And therefore, I would like to not start with spintronics data or magnetism data, but with something very different, namely microscopy of a mouse brain. So what you're supposed to see is the flow of transparent fluid through the capillaries of the lymphatic system. So that's something quite interesting. So if you take the mouse and you have the head of the mouse, actually quite recently, so I think only 10 years ago or so, there has been discovered a new anatomic organ in the mouse brain, which is responsible for waste clearance. So something like Alzheimer's disease, where you need to clear the waste. And this has just been discovered recently. And one problem is this word transparent. So you cannot see something transparent in microscopy. So, but if there's flowing some fluid, then there might be some latent impact on the data. So if you start to use denoising tools, then you might eventually see some sort of capillaries where the fluid is going through arising here. When you use the GMM tools that have been developed for example, to capture the black hole, or that has been used for the black holes, then you start to clearly see these capillaries, so the latent impact of the flow of the transparent fluid. So we have also analyzed these data by our means, and what you see is that the latent entropy resolves much more from these data, not only the surface capillaries, but also deeper lying bulk capillaries in the system, where you have some part of the lymphatic system. So for the magnetism part, we have looked at the Ising model, the micromagnetic model, and magnetic imaging data, so experimental data. And before I show you these, let me give you one slide about what is actually then the latent entropy and the latent dimension. So this is a bit more mathematical. So let's say we have two data sets, X and Y, so meaning the image frames subsequent in every image, then they can have no relationship to each other. So X being independent of Y, which is typically, for instance, if you throw a dice and flip a coin, the case. So they have nothing to do with each other. They can be rather fully dependent on each other, like when you have a rabbit and fox population, and then you need Markovian models to describe them. Or, and something that you need to know is if you then want to describe this transition probability, then you certainly need a sort of big matrix to store the information. Or you can have something in between. So not fully independent, not fully dependent, where you have some sort of hidden or latent process in the middle. And the cool thing is then that the information that you need to store reduces a bit. So you have an information matrix here and an information matrix there, and then you can have it that the information, the effective information is reduced. So to just give you a bit of a different statement about this latent processes. So let's say we have different outcomes of my dataset X. They can be mapped to a certain latent variable, which can also have certain outcomes, and then to a certain variable Y. And the first part here tells you about memory, and the second part is the part that encodes the predictability. So for example, for the Bernoulli experiment, everything gets mapped to one variable because it has no memory, nothing, you know nothing about the system, X is not depending on Y, and here you have predictability. On the Markovian process, you don't gain anything as the latent variable has the same dimension as the input variable. So not telling anything about the details of this algorithm, so just mention that there is a concrete algorithm on how you can compute the latent entropy and the latent dimension, but there's something that we made use of also from an idea of physics principles, namely the idea of path integrals. So instead of saying that we have only a certain latent process with latent dimension 3, we allow for all latent processes with all latent dimensions, and then weight their correspondent latent entropy and latent dimensions with the probability to occur, similar to path integrals. So let me show you the results for the Ising model. What we did actually, we took a small box and we changed the exchange constant in the Ising model to a small amount. And then what you know is when you compute the mean below the critical temperature, then where it's less ordered, you get a smaller amount of the magnetization, and then from that you can reveal a little bit where this box is. But if you go above the critical temperature where the Ising model orders, then the mean will not give you input. So we have looked at lots of other measures, but what we find is that the expectant latent entropy still resolves this box even above the critical temperature. And this to a rather consistent level. So even if you increase the temperature quite high and you change the relative size of the heterogeneity, so the change in this J, then you can still do very good pattern recognition with this latent entropy. And if you look at the computational time as a function of statistic size, it does not grow, in contrary to GMM. So we have also looked at a micromagnetic model, and here I do the opposite. So I don't show you where the inhomogeneity is. I just show you the fluctuation data, or one example of the fluctuation data. And probably you haven't seen much, but what we actually did is that we chose a micromagnetic model where we changed in the middle the anisotropy by 30%. And then looked at methods to find kind of this anisotropy region. And again, in the mean, we can find it, but in the Z component, because it was all out of plane, the X component is not so helpful in the mean. The autocorrelation is also not so helpful. The mean square difference still resolves it in both, and the latent entropy also. What we did then is added even more noise to the data, even on the size of the data. And what we find is that the latent entropy is not responding to the noise and still resolves the signals and still resolve and is able to recognize where this box is. And to the last part, we have applied it now to magnetic imaging data, so MOAC data, with the idea that we go from a very controlled system, the Ising model, to a less controlled system, to something where we have real experimental data and we do not fully know what's going on the subseeding structure. And this is an experiment that was done in the CLOI group to shuffle these skyrmions around and to see the thermal motion of them. And what you can already see is that, for example, this warm domain is not moving, so there's for sure a strong material defect. But with the latent entropy, we are even able, and the latent dimension, to resolve very weak material inhomogeneities and to also find kind of a superlattice structure, which is a signal of the video compression that they used. And this resolves the inhomogeneities in the data. We have also analyzed an earlier experiment from the Axel Hoffmann's group, where the idea was not focusing on very clean samples. So here the idea was on blowing skyrmion bubbles. And here we are able to resolve also in the mean, but also in these latent tools, a lot more material inhomogeneities. And as an outlook or as a summary, we have developed 2 low-cost tools for the extractions of latent pattern that work for any movie data. And as an outlook, we're going to do a strategic categorization of magnetization data. So that's something that Sarah Jenkins is planning to work on. So with this, I'm at the end of my talk, and I would like to thank you for your attention. I've talked about Skyrmion reshuffler for stochastic computing, Skyrmions for reservoir computing, data analysis tools for microscopy, and I would also like to give a big thanks to my team, as well as for this family for support. Thank you very much.
Okay, thank you so much, Karin, for this wonderful overview of your recent activities. I'm really grateful for this lecture. I'm an experimentalist, and I must say that I enjoyed. I learned a lot of things. So really nice. Thank you so much. So we can take some questions. Well, maybe I can just begin with. So when you say in the second part, just few slides before, you mentioned about the TC, the critical temperature. So is it the Curie temperature or it is some other critical temperature?
So the Ising model has a Curie temperature below it, which it's ordered, and above it's disordered, right?
Yeah.
So it's the ordering temperature of the Ising model. Okay,
okay, cool. And then when you actually look at these Skyrmion bubbles, so to say, from Axel Hoffmann's or the recent work, I'm very much aware of that. How do you actually evaluate this latent heat and the entropy? So what experimental you do, or you just take the picture and kind of convolute to this analysis? So I missed it. I'm sorry, I'm asking.
So I also didn't explain it. So what we do is
could you kindly share your screen? Because
yeah, sure.
Screen. Yeah.
I can probably share the full screen. You mean, for example, these data, yeah?
Yes.
So what we do is we have MOAC data from the experimentalist, which basically mean that we have pixels and which have a certain gray value. So these are our input data. So for each pixel, we have a certain gray value that is fluctuating over time. So when we look at the movie, then, for example, if you would zoom in, then you see that this pixel here changes from white to dark gray, middle gray, and so on over time. So these are the values that we use and that we then take as an input for the image sequence.
Oh, well, I don't see, I cannot hear anything. Others can hear her or not?
Yes, I can hear you.
Okay, now I can hear you. I'm sorry, there was something happened.
Okay, there was probably, so maybe I explain it again. So yes, we get the MOAC data from the experimentalists, which basically is for us then some sort of gray values. So every pixel has a gray value, either it's white or black or gray or a little bit gray. And this is the ones that we use over time as input for our algorithm.
Okay, that I understand. I mean, we do rigorous record microscopy, so we are very familiar with this. So, okay, you are taking basically kind of some digitalized values for the grayscale.
Yeah.
Pixels. So you are doing pixel by pixel analysis, and then from that, you are kind of developing the algorithm. And okay, so this is a kind of statistical phenomena, and you are looking at some kind of evolution of the pixels. Okay. From that,
so you could just look, for example, at one pixel. Sometimes we couple them to get a bit more of the interactions into account. So I'm not sure if I have it somewhere in the slides. I might or might not. Yeah, for instance, like this. So we take as input the different gray values, but sometimes we combine them to cross, so not only one pixel. So this is the input data, these are the different gray values, and then we use this on how it transitions to the next image, and that's what we analyze.
And how this like entropy you calculate?
Yeah, so it is a 3-step calculation. And let me show you the algorithm. So you have some certain input data, which is picture frame 1, and then Y is picture frame 2. Okay. And first you compute this relation matrix. And now we have a lot of picture pairs because you always use picture 1, picture 2, then picture 2, picture 3, picture 3, picture 4. So you have the statistics behind it. So for this, you compute this relation matrix. And for that, we just rely on literature. So there is something called a direct Bayesian model reduction algorithm, which we use. And this has been shown to be also optimal. Then we compute posterior probabilities. And for this, we use Aka-Ika weights, okay, for the entropy parts on each of the latent entropy dimensions. And then we combine them by kind of like an average, or having this path integral idea that you allow for all type of latent information.
Okay. So in principle, thanks. So in principle, let's say now there is a random distribution of skyrmions, but there may be some kind of correlation length. So that also you can evaluate, isn't it?
So right now we use the dynamics of the magnetization, which could be skyrmions, it could be just random fluctuations, to learn something about the underlying magnetics, the underlying sample. For example, where there are impurities. Or what we can also see, for example, if you look at this latent entropy, then you would probably say here it's more yellow and here it's more blue, or more green and more blue. So you know that there's a difference in the predictability. Of course, it doesn't tell you precisely what, but this one, how it's looking, it looks very much like a temperature gradient that is present in the sample. So you also see that here's a strong material defect.
Okay.
And they are material defects. You don't know which ones they are, but you know that there's something which is not homogeneous. And this is something that you can, by just the mode measurements, resolve directly. Because how these skyrmions are fluctuating, you can just think of a very simple idea, which is basically shown in this frame here. So this is showing like how the skyrmions, oh, this didn't work. This is showing how the skyrmions start from one position and then wiggle around.
Yeah.
Okay. And if it would be total random walk, then there would be no position that is preferred. But what you can see from this plot, that there are positions where there is some accumulation, so where they stay longer. And these are positions where you have impurities. And based on the time fluctuation in the magnetization data, you can infer back to where you have impurities. And based on these latent tools, you can learn about the nature, whether it was more memory or more predictability.
Okay, all right. Thank you so much. But maybe I can take now some questions from others. So anyone has a question, please unmute and ask.
Can I ask a question?
Yeah, please, go ahead.
Since the skyrmions are behaving like a particle, Could you tell me in the diffusion dynamics, what is the interaction that causes it? Do they behave like rigid bodies, or it's a long-range magnetic interaction?
Okay, so whether skyrmions behave like rigid bodies or not depends, of course, on the material or the interactions which you look at. So either from theory or from experiments. So if they are rather rigid, then maybe we can go to some. If they are rather rigid, of course, then they can be described more like a particle. But you know that they also have some sort of excitation modes. So which is the breathing, and there are also some other excitation modes which are even nonlinear.
Basically, they're breathing, right? All the time.
For example, they are breathing. Yes, they can also gyrate. They can also elongate a little bit or get like triangular shapes and so on. And it depends on which length scales you're working with. So here they are basically like a dot. Of course, if you look more into the details, then they will also transform. So this is, of course, something that we also see in the Reservoir computing project, that they transform depending on what I do with them. So here they elongate because of having some impurities or grain structures below. So whether you work with the particle light picture or whether you need more information depends on what you're looking at.
Thank you.
Okay. So Chandrasekhar, you would like to ask or should I read?
Yeah. So very interesting talk. I would like to ask something that, so those skyrmions, right? You have captured to understand the dynamics, right? Using this your algorithm. What are the time scales that are required?
Could you please repeat? Could you please repeat the question?
Okay, I will read it. I think he has some microphone issues. What are the time scales at which we need to capture the core microscopy images to understand the dynamics with the latent entropy method? So I think this is a more technical question. Like I think core microscopy, my core microscopy and Matthias Ploy almost similar. It's evicomagnetics. So the maximum capability, I think, is 16 images per second. So I think he's probably asking like, what should be the minimum or maximum time scale between different images, how fast it should be or how slow it should be, so that you can analyze those images.
So the nice thing about these latent tools is that they are neither restricted to a length scale nor to a time scale. So we have applied them to various length scales, starting from tiny length scales, even to like, we also, I think, I'm not sure if I have it here, even to like astro length scales. And we were also able to, even from an amateur video, to resolve some parts that you can also see nicely in a Hubble telescope image. So this, of course, that we didn't have much data. So they are not restricted to anything. But what you are asking maybe for is which type of information do you get out? And of course, if I take more pictures, then I get more information also on the timescales that are involved. So because what I see in these data is kind of, I reveal a certain time and space directly, but the other effects that happen have latent effects on this data that I preserve. So for example, here, I cannot resolve the impurities directly, but the impurities have an effect on where magnetic skyrmions like to stay. So of course, the more the better in a sense, because then you can capture more of these effects. But what we need in contrary is really a certain statistic size. So like 10 images are not enough, so 1,000 would be good. So it's more about having a long video and lots of data.
Yeah, I think that kind of answers the question, I hope. Thank you. Question by any others? Please unmute or raise your hand or whatsoever, or write your question. Okay, so maybe I can just ask a similar question related to one of your introductory slides to avoid this Skyrmion Hall effect. Obviously, the synthetic antiferromagnets are coming up quite nicely. And the antiferromagnetic skyrmions, it's also another nice idea. And mostly antiferromagnetic skyrmions are done by simulations. But atomic, I mean, we know that atomistic simulations are better or probably ideal. But what about the micromagnetic simulations for antiferromagnetic skyrmions? Do we have already the capability and it's already implemented and so on? Or could you tell a little bit?
So I think it depends. So a lot of groups have built now private codes to model antiferromagnetism. And the other part is about what is publicly available and what's available open source. So for sure, people have started to model antiferromagnets on a 2-sublattice degree of freedom, or build also other models that go beyond and that are specialized, and then solve the LLG equation. If you just want to use standard tools in a sense like Mumax, and also the Mumax team is also, of course, working on antiferromagnetics. But if you want to use it in a standard way, then you can go into a very restrictive coupling limit. So if you assume a very strong coupling of the antiferromagnet, then the picture reduces back to the Néel vector. And then you can describe the Néel vector kind of similar as a ferromagnet. So this has been for sure done quite often at the start. So people have used ferromagnetic code and went into the limit where you can describe the antiferromagnet similar to a ferromagnet, but just replacing it by the Néel vector. Yeah, and of course, to have it publicly available and open source, I think there is still a bit of work that needs to be done.
Okay, thanks. I mean, I know that there are specialized private codes for this, but yeah, I think people like me who are experimentalists have very little knowledge on simulations. So the public available codes, I think for us would be good. But I'm sure probably it will take some time and things will get better. Okay, so do we have any other question? If not, then if you could kindly stop sharing. I like to share the screen to share some small token of appreciation to you for our talk. So do you see my screen?
Mm-hmm.
Okay, so I just read a digital plaque prepared by our team. So W2S seminar webinar series on spintronics, National Institute of Science Education and Research, NISA Bhubaneswar, India. Takes pleasure in presenting this plaque to Professor Karin Everschor-Sitte from University of Duisburg, Germany, in recognition and appreciation for being a valuable speaker to give a lecture on magnetic skyrmions for unconventional computing and revealing latent information. Thank you so much, Karin, for your very nice talk. And it was really very illuminating and very informative. So on behalf of again of my team, I thank you and thank all the participants for joining. And next week, we will have lecture by Professor Stefan Blugel. And I'm looking forward to see you next week. So with this, we close and please stay safe. Thank you so much. Bye-bye.
Thank you.
Bye.
Bye.